Yeah. Corny jokes and rails. That's all I bring to the table.
Hey folks, really glad to have you here from Austin High School.
I think there's another school in here too.
What's that again?
Is there another school in here?
There's
too?
another school here too?
Yeah,
I
okay.
think that's right. Have we got multiple representatives?
I don't think so. No, just Austin.
This is all Austin.
I'm sorry.
Perfect. So mostly high school juniors taking AP Physics? Okay, perfect.
Nice.
Did some of you get to sit in quantum mechanics a few minutes ago?
Nobody.
I heard we scared a few people with quantum mechanics. Well, you guys have landed in not one of the last courses we teach, but one of the first courses we teach.
Nice.
So my name is Professor Walker, and you're sitting among some of our very newest physics majors who are in the physics boot camp. And the physics boot camp is a ramp up to jump straight into our physics degree. It's sort of a math review, but it's a math review of all the math that you're going to need in your first 2 years of physics in the context, as much as possible, of physics and engineering applications. So we're going to do a little trigonometry today. We've been doing trigonometry for the past few days. And we're going to look at an engineering problem here to start off with, and then we're going to start talking a little bit about circular motion and radians. So I'll bet most of you have at least seen some of this stuff here or there. So this should be something you can follow along with real well. We're real glad to have you here. So let's start off this morning with a problem that's called a statics problem. So statics means what, do you think? You can talk. What do you think?
The object is still.
Yeah, stationary, that's right. So statics would be applied, for example, to maybe a bridge situation or some situation that you want in balance. More specifically, what it means is that we want all of our forces and torques on the system to be in balance. So let's imagine a scenario, for example, where we've got a rope that's tied up at a couple of spots here. And let's imagine that someone is maybe standing on that rope, okay? And as they stand on that rope, maybe they've got their arms out, maybe one of those balancing pulls, okay? As they stand on that rope, of course it bends down a little bit, right? Flexes a little bit and supports their load. Now, this person is the person that we want to keep in equilibrium. We don't want them to fall through the rope. We want them to be there in balance, right? We don't want them to fall, be pushed one way or another. So what we need to do in order to keep that person balanced, and we're going to kind of pretend that, even though I've drawn them as a big tall person, we're going to kind of pretend at the moment that they're just basically a little dot sitting at that point on the rope. Okay? We're going to think about all the forces that are acting on them. Of course, the first thing to consider is gravity. Gravity pulling the person down. And do you guys know what you label that arrow with to represent gravity? That person has some mass. What are we going to write next to the gravity arrow? Yeah, that's right. Perfect. So mg will be our gravitational force pulling down. Now, obviously, that's not the only force in effect on the person. If the only force were gravity, they would just be falling and accelerating downward with acceleration magnitude g, right? So the other force acting on them, of course, is coming from these two ropes. And what do we label rope-type forces with? What do we call them? Tensions. So we're going to say that there's tension pulling that way, and we're going to say that there's a tension pulling that way. Now these two tensions, we're going to label them separately as T1 and T2. And the goal of this problem is going to be to figure out what the values of T1 and T2 are to hold this person up. So let's give this person a mass. Let's say the mass is 50 kilograms, let's say. So that's about 110 pounds, give or take. A pretty light person. I don't know, I don't got to make the world's prettiest tightrope walk. A pretty light person. Okay. Let's say 50 kilograms, have a nice number there. And that means that mg, now what's the value of g? You guys know that, I think. Perfect. Okay. We're going to round just a little bit and tell you what, just to keep our number simple, let's round it to 10. And what are our units on that? Meters per second? Square, that's right. So it's about 10 meters per second. That means if you drop something every second of time that passes, it picks up 10 meters of speed, right? So 10 meters per second of speed per second, or meters per second squared. So that means their mg is 50 kilograms times 10 meters per second squared. So I think we can do that one in our head, right? Let's call that 500. And what are the units on that? Newtons, that's right. And newtons is just a fancy way to say kilogram meter per second squared, right? Because we don't want to say kilogram meter per second squared all the time, because that's the thing that you'd have to say pretty free. Now, your job is to keep our tightrope walker from dying. That's your job. Are you up to the task? Did any of you see that movie? What was it called? Where the guy walks on the tightrope between the old twin towers.
French guy.
Yeah, French guy.
Incredible.
Incredible, yeah. Well-made movie, too. You would think that it would be hard to make a whole movie out of that thing, but it's...
When the twin towers were still up.
When the twin towers were still up. Amazing. Snuck up, it's worth watching. Snuck up there, and, you know, that's a major problem to figure out how to get your rope over to the other tower, right? So they got the rope across to the other tower, wired it all up in the middle of the night, and then as the sun was coming up, this guy walks on the tightrope across the towers. You're his engineer. Your job is to make sure the rope doesn't snap. Okay? So what I want to ask you, I want you to guess and think about it for a little while here. Let me put some angles in here. Try some angles into that thing. I'll tell you what, I'm going to make this 5 degrees. Make that 10 degrees, theta 1 and theta 2. And the question is, what does the tension in that cord have to be to make sure that our tightrope walker doesn't fall? Remember, tension's a force, right? So tension's a force. And the force of gravity is going to be 500 newtons. So I want you to think, you can say a number if you want to, or you can just have it in your head. But think, what would be the minimal rating that you would purchase for this cable to make sure our tightrope walker doesn't die? Any suggestions? 1,000? Okay. So you say, okay, maybe let's double it. Let's say if the guy was just hanging from a single cord and just hanging there and not doing there, 500 would do the trick, right? The question I want you to think about a little bit is, if the guy was just hanging on the cord, now if he's climbing on it, that actually can add, because he might be accelerating up, that actually puts a little bit of extra tension into the cord. 500 might snap. But the question I want to ask you is, in this particular situation, when these two cables are balanced as such, do you think it's 500? Do you think it's 250? Maybe each of them is 500. Do you think it's more than 500? Somebody said 1,000. How many would you say way more than 500? How many of you would say a little less than 500? How many would say way more? Nobody's going way more? How many would say in the range of 500? Okay. How many would say maybe a little less than 500 because the ropes are going to split it? I don't think everybody voted, but did everybody at least vote in their heads? Okay, let's run through this thing. Let's do the math, and let's see if we can figure out what the answer is. Now, this problem is intended for us to practice a couple of things, okay? It's a physics application, an engineering application, in that sense, you know, it's sort of a simplified case, but it's a very real physics and engineering application. But it's also a chance for us to practice, as you can see there in the drawing, a little bit of our trigonometry, right? And then once we practice our trigonometry, it's also a good example for us to practice a little bit of algebra, some equations to solve. Now, it's just a little bit of physics that comes into this thing. I guess you could say that's a little bit of physics, writing the gravitational forces in G. The other little bit of physics that comes into this thing is going to come in from that very first word we introduced to describe this problem. It's a statics problem. So statics problems, in a nutshell, are problems where you don't have any accelerations. Most often we want the thing also to be sitting still, but more importantly than being still, we want it to stay still. We want it to not be changing its speed. And in addition to not changing its speed, we also usually want that constant speed to be 0. But the more important thing is actually the speed's not changing. So speed's not changing, no accelerations. If there are no accelerations, then there must be no forces. And of course, we do have forces here. We do have forces, but no unbalanced forces. In other words, if we don't want to have any accelerations, it means all of our forces have what?
Equal.
Yeah, 0 out, be equal. All of those are good answers. So they cancel. All of our forces have to cancel. And additionally, what's that little arrow mean? What's that little arrow?
Directional.
It's directional. It means that force is what? Has a direction. It's a vector. You know that word? You heard that word? It's on the tip of your tongue? You know that word? Vector. It's a vector. It has a direction. So not only do our forces need to cancel, they need to cancel in all directions. How many dimensions is this problem that we're doing? It's a two-dimensional problem. Right? We've got left to right and up to down. Let's draw a coordinate system here. Always good to say where our coordinates are. We're going to make that our x direction. We're going to make that our y direction. And in other words, what we want is for our x forces to add up to 0, and also for our y forces to add up to 0. And those will be the conditions that this system is in some balance. Now, T1 and T2, do we know them? No. The goal of this problem is what? Figure them out. Very important principle in physics problem solving. I sometimes call it the fake it till you make it principle. It means if you don't know something, you got to give it a name. You got to give it a symbol. If we don't give something a symbol, if we don't give it a name, we can't put it in our equations, we can't manipulate it. So we're going to give these things names. We don't know what they are yet. T1 and T2, but now they have names. Now we can manipulate them. Now they can go in our equations. And these T1 and T2, why don't you look what they're doing here? This T1 and T2, it's doing two things, right? Because it's pulling at an angle, it's pulling sideways and up. You see that? It's pulling sideways and up. Let me ask you something. That cord, the way that we've drawn it, is it doing more pulling sideways or more pulling up?
Sideways.
Looks like more sideways to me. I want you to think for just a second. Now, our original question was what? Our original question was, what should the minimum tensile strength of this cable be so that our poor guy walking across this gap doesn't fall? And the question was basically, do you think it's in the ballpark of about 500 newtons minimum strength? Or do you think maybe it's a little less? Or do you think maybe it's quite a bit more? Let me give you a little hint here. This cord, is most of its pulling doing up or sideways?
Sideways.
Sideways. Do you want to change your votes? How does that affect your votes? Think about it for a second. Here, let's revote. How many people say less than 500 should be safe? How many people say ballpark of 500, a little bit, give or take? Okay. How many people say you better make it quite a bit more than 500? This guy's definitely going to die. Okay. Let's do a few more calculations before anybody gets on the rope. Everybody at least got a vote in their head? Let's go through. Now our next step, we've defined our coordinate system here. Our next step is going to be to break this guy up into its components, right? So the hypotenuse is T2. We've broken that hypotenuse, the long side of the triangle, up into a little sideways and a little up. I'm going to call this T2 and T2. Hold on, I'm not done yet, of course. But both of these sides are proportional to T2, right? But then they're both a little bit less than T2. They're both a little bit less. And that amount by which they're less is a ratio that we call a, what type of function? What's this shape? Triangle. What type of functions are these? Yeah, trig functions, yeah. So what are our two main trig functions? Sine and cosine, and then we've got the ratio of sine to cosine that we call what? Tangent. So sine and cosine, you guys know, sine and cosine, all these are ratios. How much shorter is the side relative to the hypotenuse, right? That's exactly the thing that we need here. Because that's what we're asking. We're asking how much less is this than that. Yeah. So this, it starts off at that. Say we're going to make this a little bit smaller relative to that. So the first thing we're going to write is the hypotenuse. Then the next thing we're going to write is the ratio. And all that you've got to remember to get this straight is which one goes with the side that's close to the angle, the sine or the cosine. I'm going to give you a little mnemonic that served me well for many years. Close is cos. Close is cos. I recommend that you not do the, not some big long complex. That's hard to remember. It's too slow. We need to be fast with this. So I'm going to look at the angle I've labeled. And the side that's close, I'm going to write cos. That's it. The side that's not close, I'm going to do the other one. On the right side. Same thing over here. Except this one's pointed left and up. Left and up. So this side, that's proportional to its hypotenuse, but its hypotenuse is T1. That's proportional to its hypotenuse, T1. I've just got to decide which side is close. Looks like that one, right? This side's close to my angle, so it gets close. Different angle, of course. Cos theta 1. Sine theta 1. I want you to notice one other thing here. We've drawn these arrows, right? That plus that equal this, and that plus that equal this. But I've not written negatives there. I've just written the magnitude next to the triangle. And when I bring it over to the equation, when I pick it up off the picture and stick it in the equation, I don't have my triangle sitting there anymore, so I better write a plus or a minus. A minus if that arrow that it corresponded to was left, and a plus if that arrow it corresponded to was right. So I'm going to pull all my x parts together. That's an x part, right? Is it plus or minus? That's plus. And that's an x part, plus or minus?
Minus.
Perfect. So I'm going to write for my x parts, T2 cos theta 2 minus T1 cos theta 1. Is that it for my x forces?
Yes.
They better balance so they don't produce any accelerations. I do the same thing for my y's, except there's a little bit of difference here. Both of my y's are pointed up, right? Oh, and there's one other important y I better not leave out. So I've got T2 sine theta 2 up plus T1 sine theta 1 up plus mg gravity pointed. G itself is positive. G itself is the positive number. It's not the negative out in front. So a little bit of up, a little bit of down. Better cancel out so that the system stays balanced. There's one other thing I want you to notice here that I would suggest getting in the habit of is that up to this point, and as a rule, unless you're in a hurry, if you're in a hurry on an exam, maybe do the thing as fast as. But as a rule, it's usually smarter to wait as long as you can to plug your numbers. So we're going to leave our symbols there. And if we do that, then we haven't just solved the one problem with the one set of numbers, we've solved all the problems at once. That's the fantastic thing about it. and we can see what will happen if we have different values as we wait to put our numbers in. Now, from our point of view though, even though we're leaving them as symbols, the angles are given to us, right? And from our point of view, the mass is given to us, and G, of course, is given to us. So that means the two things that we're going to consider to be our unknowns, even though everything is a symbol, are what? T1. So how many unknowns do we have? Two, that's right. We have 4 boxes, but they're repeats, right? So the different things that we have that we don't know are 2. How many equations do we have? Is that a match? That means we can solve. 2 unknowns, 2 equations. Both of these are linear. So what would you say? Maybe solve that one for T2? And then once we've got that one for T2, what are we going to do with it? Plug it back into there. Let's do that. Let's solve that top equation for T2. So first thing we want to do is swipe right on that. Send this guy over there. That's going to turn from a minus into a plus. Let's divide by the cos, and we've got the T2 there. So all in one step, T2, take that negative term to the other side of the equation. That becomes a plus T1 cos theta 1, and then whole thing divided by. Now that we've got that T2 from this equation in terms of T1, I'm going to take that T2 and put it into here. Everybody track? Let's take that and put it into there. So I'm going to start off with T2, which is T1 cos theta 1 over cos theta 2. And what did T2 get multiplied with? It got multiplied with sine theta 2. And then we're adding to that T1 label that. That was theta 1. Sine theta 1. And then why don't I take this minus mg and go ahead and flip that over to the other side as well. So now we've got it where we want it. We've got it cornered. We've got one equation with one unknown. And it just comes in linearly. All we need to do, first step, take that T1 and do what? What do we call that? Yeah, combine like terms, I think what you said, or factor it out, let's say. That T1, it goes in both. Let's factor it out. So then we've got T1. Once we factor that T1 out, then everything else is going to get divided down to the other side. Right? Let's do that in one step. So T1 is mg divided by all of these other factors, which is cos theta 1 sine theta 2 over cos theta 2. All that's a factor together. Plus sine theta 1. Everybody? Now, if we want to get T2, we can take T1 and put it back here, right? Now, let me show you a little trick. You think we could already kind of guess what T2 is for T1? It's not T2. The formula for T2, can you guess? The formula for T2 has got to be related to the formula for T1 by what? By what transformation, what change, what substitution?
The sine and the cosine.
sort of getting warm. In other words, if I took this formula that I already know, right? I took this formula and I already know it for T1, but I wanted to write the formula for T2 based on it, what would I have to change? Everywhere where it says what? Everywhere where this formula says theta 1, I would have to turn it into 2, and everywhere where it says theta 2, I'd have to turn it into 1. Theta 1. Is that obvious from our picture? Theta 1 was the angle that went with T1. Theta 2 was the angle that went with T2, right? We're just trading the names. They've got to have the same type of formula. Just trading the names. Let me show you that that works explicitly. This says T2 is T1 times cos theta 1 divided by cos theta 2. If I multiply this expression by cos theta 1 over cos theta 2, I'm going to move it down to the denominator. If I move it down to the denominator, it's cos theta 2 over cos theta 1. Cos theta 2 will cancel cos theta 2. Cos theta 1 will cancel cos theta 1. This term will just turn into sine theta 2, playing the role of what that term used to be with sine theta 1. Then this will get multiplied with cos theta 2 over cos theta 1. This term will play the role that that term previously played with all the angles. We can write that explicitly, immediately, without doing any more work, by just saying T2 is going to be the same formula. Let's switch all the angles. Sine theta 1. This I better write. Let's run that up. The sines and the cosines stay where we are. Cos theta 1 turns into what? Cos theta 2. Sine theta 2 turns into sine theta 1. Cos theta 2 turns into cos theta 1 plus sine theta 1 turns into sine theta 2. Okay. That should be good. Now, before we leave this problem behind, let's get some numbers out of it, because that was our first question. Let's go back now and answer our first question. We've done our physics. We've done what I would say solving the problem is, right? You guys know solving the problem is not like it was in 7th grade anymore, right? Solving the problem doesn't mean take a formula and put some numbers into it. Solving the problem now means what? Find the formula. That's what solving the problem is. So we've solved the problem. We found the formula based on some general principles. Newton's second law, and we don't want to have any accelerations. General principles. Now let's put our numbers in. That's just like the cherry on top at the end. Let's put our numbers on and get an answer. So, let's solve for T2, let's say. mg was 500. Cos theta 2. Theta 2 we set up to be 5 degrees. Sine theta 1, that was 10 degrees, divided by cos theta 1, divided by cos of 10, and then plus sine theta 2. Now, some of you have calculators with you. Go ahead and punch that through if you like. If you don't have your calculator, I will almost never say this in my class. Go ahead and pull your phone out just this once. We've got a calculator. Turn the thing sideways so it gives you, turn the thing sideways so it gives you the trig functions and all. I'm going to suggest to you that it's actually pretty easy to enter this incorrectly into your calculator. The order has to be done a little bit particularly. You have to use some parentheses maybe. Let me suggest to you what I would say is the cleanest way to punch this into your calculator. First thing, make sure your calculator's in degrees mode, because we refer to our angles in degrees, not radians. When I look at something like this to punch into my calculator, I tend to drill into the most complicated part first. I like to do these things kind of inside out. Would you agree maybe that's the most complicated part of the expression? So the first thing I would put into my calculator would be something like cos 5 times sine 10 divided by cos 10, and then I would do something like enter. Enter is really nice. It gives you basically, it groups those terms together. It's like a parenthesis. It groups all those things together. And once I press enter, I would say plus sine 5. Now I want to group that whole block, so I'd say enter again. Then I would say, if I had one of these calculators that had the previous answer key on it, then I would say 500 divided by answer. Or if I didn't have a calculator that did that, but maybe it had the 1 over x button, I would hit the 1 over x button because I've got this block evaluated, but what I really want is 1 over that block. So I might hit the 1 over x button, then times 500, and we would have gotten real clearly to our answer. Okay, let's see if we got the same numbers. What numbers did you guys get? Say it. I'm sorry, I can't hear it.
1,902.5.
Anyone get that as well? Several people are getting that? Say 1900. And then T2, let's compute that. 1900 times, that was cos 10 over cos 5. Done it backwards?
Yeah.
Oh, I do have it backwards because we already solved for T2, right? And I want T1. Thank you very much. I want T1 is T2 times cos theta 2 over cos theta 1. So T2 we solved for, which was 1900. And then times cos 5 over cos 10. Get the right way around now? What have we got there?
1,922.
Pretty similar. Our angles are not wildly different from each other. What did we find out? How many of you killed our tightrope on? Our tightrope.
Probably a lot of people.
Well, we have a lot of falling tightrope on.
Yep.
What did we find out?
A lot of tension.
It takes a lot of tension. Now let me give you some intuition into that. I think several of you have got it figured out. After you string your rope across, if you watch the movie, what do these guys do? They turn a crank. And as they turn the crank, what's that rope doing?
Go down.
Getting more and more. Imagine flicking the thing. It makes a sound right. You turn the crank, what happens? It's tighter, higher pitch, right? And as it's getting tighter, imagine if the guy were standing on it while you turn the crank. You turn the crank, you're adding more tension into the system, right? More and more tension. What's that rope doing? It's getting tighter and tighter and tighter as the angles are getting smaller. Now, the nice thing about having these formulas, and I'll leave you to check them if you like, but the nice thing about having these formulas is we can go back and check other angles. If theta 1 and theta 2 were both 90 degrees, if they were both 90 degrees, that would just be the guy hanging from the rope, right? What do you think you'd find for the tension in each cable? Not each 500, there's 2 of them. Each one 250. Just check that in the formula. But then if the angles get really, really small, look what's happening here. What's sine of 0?
0.
Yeah. What's sine of 0? 0. What happens when you divide by 0? The universe ends. Sometimes we say infinity. In other words, what? If you want to get that cable to go all the way up parallel, how much tension are you going to have to put into it? All the tension. A lot. Are you ever really going to get it parallel? No. But it's going to be very sensitive to those angles. If the guy's just hanging from the rope 250, you'll do it. And then you raise the angles a little bit, not much happens, ooh, it's getting harder and harder to raise anymore. And that last little bit gets incredible. And that last little bit getting hard, you can think of as that sine theta getting really small. And there's another sine theta there. Both of those are getting small. And we're dividing by something that's really, really small. The cos thetas are both going to 1. So these are canceling. And then we have the sum of two sines, and if both of those angles are really small, we're dividing by something really small. The whole thing's getting really big. To see it in picture form, most of our pulling is going sideways. I think several of you saw this picture again. Just a little bit of it's going up. We need that up part to cancel gravity. In other words, this plus this has to be 500. If that angle is small, this is obviously a lot bigger than that. Making sense to everybody? That's the intuition. So let's see how we're doing on time here. It's just enough time, I think, to start to, about 2 minutes here, to start to introduce this other idea that I wanted to bring to the class. So radians is the other angle, is the other idea that we want to talk about for a few minutes. Radians somehow can be a little bit of an intimidating issue when you first encounter it. It seems a little weird. I want to convince you that it's real, real simple, real easy to do. Make sure everybody understands radians 100% in the next 10 minutes. Now, we use degrees more often than not in conversation, right? How many degrees in the full circle? 360. Why? Why? I don't know. Whatever. Let me give you some ideas. For one thing, 360 is a number that's real nicely divisible. It divides by all the numbers. Divisible by 1? Yeah. By 2? Yeah. By 3? Yeah. 4? Yeah. 5? Yeah. 6? Yeah. 7? 7's a toughie. 8? Yeah. That's 45. 9? Yeah. 10? Yeah. 11's a toughie. 12? Yes. 13's a toughie. 14? I don't think so. 15? Yeah. It divides nicely by a lot of numbers. I suspect, you can look this up, I suspect that it's also that it's very close to the number of days in a year. So you could say that, as the Earth makes its transit around the sun, and the sky that is visible is also changing as you move around by about a degree per day. Let's suspect those are also connected. But basically, what's the point? Basically, the point is that 360 degrees is completely what? Completely made up. It's arbitrary. It's a good enough system. We can agree to it. We can communicate. But why is it 360? Because somebody said it was 360. Is that a very good reason? Not the greatest reason. Is there another system? The question is, if you're just going to replace it with another system that's made up, then maybe you don't want to have two systems that are made up. But the question you might ask yourself is there a more natural system? And the answer, of course, is that there is. And that more natural system is radians. So, let's draw a picture here. Have a circle. Break it into X and Y. Have some radius here for the circle. We have some angle, and we have some little distance along there. It's called the arc length. And what symbol more often than not do we use for arc lengths? Say it again. I'm not sure I heard it. Yeah, arc length. You know what symbol we use more often? It's a letter. S. Several ways. S more often than not is what we use. Now, if we go all the way around, all the way around once, the arc length is just equal to the circumference, right? So the circumference, what's the circumference relative to the radius? 2 pi. So we would say it this way. A circumference has 2 pi radius lengths. We'd say a circumference has 2 pi radius lengths. So in other words, once that angle has gone all the way around to 360 degrees, our arc length has become a circumference. It's gone 2 pi radius lengths around. We say 360 degrees is 2 pi radians. So the angle in radians is just how many radius lengths it takes to get around. The way that I've drawn it there, this is 1 radius length, right? How many radius lengths is that just by inspection with your eye? That compared to this, just maybe a half. That might be half a radian. This might be 1 radian. This, then that might be 2 radians. Then 3, then 3.14, 5.59, blah, 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 blah. 3, 4, 5, 6.28. 2 pi radians to get all the way around. So this is the way that we say it. In equation form. The angle in radians is just the arc length measured in radius lengths. The angle in radians is how big is the arc length compared to the radius. If it's 1 radius, 2 radii, 3, that's the angle in radians. Now, how to convert? How to convert back and forth. Real easy. You guys are getting geared up for SAT, right? Do they still do the this is to that questions? This is to that as this is to that. Is that still the thing? Theta in degrees is to theta in radians, as what is to what? Theta in degrees is to, what's the full circle in degrees? 360. As theta in radians is, what's the full circle in radians?
2 pi.
That's it. So if you want theta in radians, you go 2 pi over 360 times theta in degrees. More often than not, that gets remembered as pi over 180, but that's the reason. And then if you want to go the other way, it's 180 over. One last little thing today before we break. This is real important. In boot camp, we're going to come back to this several times. This is a real big idea. What we want to talk about for just the last little bit here is what's called the small angle approximation. Now, the way that I've drawn that, depending on your definition, qualifies as a reasonably small angle. Let me show you something. I'm going to box off that triangle. I started off with a wedge of pi, right? Like PIE. I started off with like a wedge of a slice of pie, right? But I'm going to lop off that edge there and turn it into a triangle. This side is the adjacent side, or the close side. That side is the hypotenuse relative to my angle. That side's the opposite side. Sine theta. Sine theta is what? Opposite over
adjacent.
adjacent. And,
Hypotenuse.
Yeah.
Catch you.
Thank you. Tangent is what? Tangent is?
Opposite over.
There we go. All right. Somebody awake here. Opposite over adjacent. Now let me show you something. Just look at this picture here. Our opposite side, that's pretty similar to what? It's pretty similar to S, isn't it? And our adjacent side, as long as the angle is not too small, that adjacent side is not so different from the radius, in other words, the hypotenuse. So sine theta, which is opposite over hypotenuse, is approximately equal to S over R.
Maybe you gotta mix up again. You're saying hypotenuse, okay, my bad.
What is it?
Because I just saw the adjacent on my phone.
Okay. So S over R, opposite S, hypotenuse over. S over R is otherwise known as what? The angle in radians. And same thing here. Opposite over adjacent. Opposite is S. Hypotenuse is just about the same as adjacent. And the hypotenuse is R. So once again, S over R. For small angles, be careful, this doesn't work in degrees because it used the definition of what? Use the definition of radians. But check this. Let's get our calculators out one last time. Put your calculator in radians mode. Put your calculator in radians. Type sine 0.001. Sine 0.001. It should be in radians mode. What do you get back? Basically the same thing. Let's make our angle a little bigger. Take sine 0.01. What do you get back? Pretty close to what you put in,
Yeah.
but it's starting to differ a little bit. Put sine 0.1. Differs a little bit more, but still pretty close.
Yeah.
Cool. Let's do sine 0.2.
0.199.
Not too bad. Well, yeah, it depends on how much accuracy you inaccuracy you can tolerate. How about sine 0.5?
0.479.
Okay. That's pretty close to the angle that we drew, remember? This is about half of that, roughly, right? How about sine 1 radian?
0.84.
Okay. It's getting worse. How about sine 2 radians?
That's way out.
Way off? Yeah, if we go all the way around the backside of the circle, sine 3 is just going to be wildly wrong. But what we're going to learn about a little farther along in this class are something called Taylor series. I'll leave you with this. So sine theta, the first term in the expansion is theta. There's another term in the expansion. What's that? There's another term in the expansion. What's that? You know what these factorials are? 5 factorials times all the numbers small of you. 5 plus 4 plus 3 plus 2 plus 1. And then can you guess what the next one is? Is it plus or minus? Minus theta to the 7th divided by 7 factorial. Put that into an Excel spreadsheet. Play around with it a little bit. Plot it. If you take it out to enough digits, guess what you'll find when you plot that as a function of theta? This, and then finally, if you don't take it to enough digits, it'll go crazy. But you'll start to get that oscillating curve back. That's called a Taylor series expansion. We'll see a whole lot more. So glad to have you guys with us in class today. Thanks for paying good attention. Thanks for keeping me on my toes. Let's go have some lunch.
All right. Are you in video or? Next year. You and Rico?
Yeah, we're seeing.
You seen this? Did she talk about small angle? You saw it already? I always wondered where that came from. Now I know.
Awesome.
Small angle
Awesome.
approximation. That was very nice.
Yeah.
I love the basics of radians.
Yes.
You know, you have gaps.
Yeah.
You know what
That's
I
right.
mean?
I know what you mean. I know exactly what you mean.
You know what I mean?
Well, I've got more than I'd like to.
Well, I have my biggest business is actually thermal.
Yeah. That is, thermo and StatMech is just it's its own little island of strange ideas, isn't it? And I enjoy teaching it for that reason, because every time I come back to it, you're just so different from anything else.
I haven't taught it in years.
Yeah. But that's the right way to learn it.
Maybe we'll grab my team. Thank you, Dr. Walker.
Thank you.
It was excellent.
Appreciate it.
Hello. Did somebody say lunch?